So let me give you a philosophical background. We believe very strongly that all of formal education, all classroom-based education has one core goal, and it's true from the time our students are coming into the pre-K pipeline until they exit. And we hope that the vast majority of our students graduate high school. We hope the vast majority of them go on to an undergraduate institution and graduate. And we hope that a percentage of them go on to graduate school. But when they graduate, they're going to get a handshake and a diploma. And what the handshake is going to let them know is congratulations, you're on your own in the real world. That's where they're going to spend the rest of their professional careers, on their own in the real world, which means that all of formal education is about preparing our students to enter the real world. And in the case of STEM education, we hope that we can inspire some of our students to want to go into science and technology careers. And what's really important there from the standpoint of STEM ed is that it's important for our students to understand what is expected of professional scientists and engineers so that they can make informed decisions about career pathways, which means that the students need to know what is expected of scientists and engineers while they are still in formal education. And we feel very strongly that the best way to do that is to take a real world experience, bring it into the classroom, and allow our students to be scientists and engineers right now. And that's what this program is all about. And another aspect of this that I think is really important is you might say, well, do I think that students right now have the ability to be scientists and engineers? Is that a tall order? Well, it's not, and let me explain why. If you ask scientists and engineers what they get paid to do, they're going to tell you that they're paid to ask questions. They have to be naturally curious about their world, and they are paid to ask questions. The way that we say that in formal education is that they are inquiry-based learners. And the other thing that they will tell you is, well, to answer those questions, we create experiments and pathways to find an answer, which usually involves securing data and evidence from the world around them. They need to poke their world in a well-defined way to secure data and evidence that they can interpret so that they can understand how the world works and see if they've answered their question. So they are evidence-based learners. And then you put that together, what scientists and engineers do is inquiry-based, evidence-based learning, which we falsely call the scientific method. It is a process for exploration. And the reason why I say it's not correct to call it the scientific method is because inquiry-based, evidence-based learning has nothing to do with science. It's how humans learn, and it should be supported in all subject areas. And why do I say that? Well, I know that some of you are parents, and you remember the magic time when your kids were first capable of expressing themselves. And you know that's when the unending stream of questions began. As soon as we're capable of expressing ourselves, we start asking lots of questions. We are born to explore. We are born curious. We are born to ask questions. We are born inquiry-based learners. And the other thing that parents remember is when we remember our infants, they love to poke their world. They explore near versus far and up versus down and color and texture. And the act of poking their world is the act of demanding evidence in return so that they can interpret the world around them and figure out how the world works and how they successfully navigate through that world. So we humans are born evidence-based learners. We are born inquiry-based, evidence-based learners, and that's what our scientists and engineers do every day of their lives. And an artist or a chef or a teacher or a lawyer, professionally, they are doing inquiry-based, evidence-based learning. So if you bring a real-world experience into the classroom and you ask our students to be scientists and engineers right now, it should feel very natural to them. So everybody with me on this so far? Does this all make sense? Okay. So the point then is that we are born to learn through a process-based approach, which is antithetical to the way most school systems, for instance, in the United States teach, which is to aim a fire hose of content at our students' heads and ask them to memorize everything. That is a content-driven approach. It has no bearing in the real world whatsoever because that's not the way we learn. It removes ownership and learning from our students because it's the teacher that is dictating what they should be curious about. And so the whole idea is to recognize that formal education ought to be focusing on process-based learning, and content goes along for the ride. And if you ask what are the skill sets associated with process-based learning, what feels natural, ownership in learning. The student has to own that experience, otherwise you take that away from them. We cannot beat the curiosity out of our students. Problem solving, critical thinking, the ability to navigate an interdisciplinary landscape to secure the core knowledge necessary to solve a problem at hand, and the ability to communicate your thoughts and ideas orally and through the written word so that you can talk to your peers and colleagues and get team think going. So communication skills are very important, and the ability to work in teams are very important. So does everybody understand the philosophy of approach and the skill sets that we want to reinforce in the context of that philosophy? Thumbs up? Okay. And we had an informational Zoom some time ago when Laura was first interested. Was any, besides Laura, who else was on that informational Zoom? Okay, so Miranda was on it, and we covered a lot of this material. And one of the things that we found out is this is a good fit from the standpoint of philosophy of approach, hence why we're having this conversation now to get you launched on the program. So what we're going to do today is just a summary. I'm going to give you an overview of SSEP and how it mirrors that philosophy of approach. We're going to go over the program critical timeline and how the program is implemented. I'm then going to go into classic experiment design, and then I'm going to go into microgravity experiment design. And so let me just pause here and say, how many of you have any experience in designing microgravity experiments with students? Raise your hands. Okay, nobody. And by the way, Terry, it would be really great if you could turn on videos, because I should be seeing a class, not disembodied names. And so, and you're going to be participating, and I need to see your reaction, and I need, it's important for me to see you.
For sure. I'm the principal here at Naismith, so I'm just jumping in and joining for a little bit, and then I have a meeting at 9:30. So I was just kind of just staying out of it and listening in to see what's happening.
Okay, sounds good.
Okay,
So
thanks.
because you don't have a background in microgravity experiment design, that could be a very scary term to you. I don't know what a microgravity experiment is, so I have to allay your fears. I have to show you that a microgravity experiment is a really simple concept, and it grows very formally from classic experiment design. So we're going to go through a review of classic experiment design, looking then at what a microgravity experiment is. We're going to look at how the mini laboratory operates and 5 ways to get students excited about thinking, what experiment would I like to do? And then we're going to go into the website navigation. So we're going to go through this overview of the agenda. So let me say one last thing that I forgot to say before. If you're going to bring a real world experience, hopefully from the frontier into the classroom, and allow our students to be scientists and engineers right now, it really should capture what scientists and engineers do in a comprehensive way. And one aspect of that I think is really important is if you go to a researcher's office, you're going to see computers on their desk. If they're experimentalists, you're going to go to their lab and you're going to see expensive laboratory equipment. They're going to have to go and travel to conferences to present. They might need access to a supercomputer, a super collider, a telescope, and all of those collectively are what we call research assets. And the way that those assets are typically gotten is that a federal agency, I'll give you an example in the United States, a federal agency like NASA or the National Science Foundation has a precious and limited amount of research assets, typically grant money, in a very specific discipline. Never enough to go around to all researchers that want to use those assets. So the way that the federal agency gets that asset out in an equitable way is they issue a national call for proposals. And research teams all over the country, in absolute secrecy, design a research program around the asset they're trying to secure. And they write a formal proposal against what's called a proposal guide to make the case for why they ought to get that asset, as opposed to all of the other teams. And so if it's NASA, NASA will take all the proposals together. They will convene a review board, and the review board will strictly grade all of the proposals using the proposal evaluation rubric that was in the proposal guide. And only the proposals with the highest of grades get an award letter, and everybody else gets rejected. They get nothing. And it doesn't matter how hard those teams worked on putting the proposal together. So the way that real research is done is through formal competition. And the competition is very stiff. And so how does this connect to STEM education? Well, let's say we inspire some of our students to want to be scientists and engineers, and they get that last handshake and they're out in the real world, and only then do they say, wait a second, you mean for me to be a practicing scientist or an engineer, I have to compete? Nobody told me that. And for me to be a practicing scientist or an engineer, I have to be an absolutely superb technical writer? Nobody told me that. And if that's when they're finding out, we in formal education have failed them because they're not ready for the real world. And so if you're going to bring a real world experience into the classroom, we feel it would be nice to be a comprehensive experience, which includes a real research proposal competition. Not as a brutal competition, but as a series of teachable moments where students get to say, oh, I didn't know scientists and engineers have to compete for resources. I didn't know they had to write technical papers like a proposal with embedded citations in the text and a bibliography of primary references. I didn't know what a research proposal competition was all about. These are a series of really important teachable moments that also allows a school and school district to reinforce their technical writing portion of the curriculum, because in STEM education, if you don't have a technical writing portion of the curriculum, you're missing something really, really important. So does everybody understand this extended sort of philosophy of approach here? Okay, so now I'm going to pause the recording. Okay. So what I'm going to do now is I'm going to give you an overview of the Student Spaceflight Experiments program. And again, we're trying to grow a program that grows organically from that philosophy of approach. So we're going to give your school district, and there are 3 schools participating in the program, your own real space program. And what that means is you're going to get a flight slot to fly one of your student team designed experiments to the International Space Station and have the astronauts operate your student experiment according to the student flight team's protocol. They are simply your technicians. You are not competing with any other community participating in this program. Every community has one student team designed experiment operated 250 miles above the surface of the Earth. And so the way that this is done is that after you go through a formal microgravity curriculum with your students, you break your students up into teams of 3 to 5 students per team. And then you're like NASA. You have a precious and limited research asset. You only have one student flight slot to fly an experiment. You have a lot more teams than that that want that flight slot. So you have a precious and limited research asset, one flight slot. So you issue a local call for proposals to your student teams. And all of your teams in absolute secrecy then design a microgravity experiment and write a formal proposal to make the case for why they ought to get your flight slot. So let me tell you how the STEM comes together here. The first thing is that each team is going to design a science experiment in a science discipline of their choice. They own this. And the next part of that is that the science experiment needs to be constrained by the engineering that is imposed by the flight certified, easy to use mini laboratory, and that mini lab must be used. So its engineering constrains the design of the science experiment. And the design of the science experiment is going to be constrained by the technology of flight operations to and from low Earth orbit. And the experiment itself is going to be characterized in terms of volumes and concentrations and pH and data analysis. So it's going to be characterized through the language of nature, which we call mathematics. So that's how you get an integrated STEM authentic initiative. Everybody good with what I just said? Does that make sense? Yes, no? Okay. Now, let me give you an example from the real world. So my PhD is in astrophysics, and my specialty is planetary atmospheres in our solar system beyond Earth. And let's say I want to use a huge telescope on the big island of Hawaii on top of a dormant volcano called Mauna Kea, and I want to measure the global winds on the surface of Mars. And I want to use the spectrometer, a very powerful instrument that they make available to researchers like me. The first thing I have to do is get the operating manual for the spectrometer, which has all of the engineering and technology constraints imposed by the use of this instrument. Another way to say it is the operating manual for the spectrometer tells me what it can do and what it cannot do. And only once I know those restrictions can I start thinking about designing my science experiment, because it makes no sense at all to put together a science proposal and submit it to the time allocation committee if they review it and they say, well, our spectrometer can't do that. You didn't do your homework ahead of time. SSEP is the same. There is a mini laboratory operations page that has all of the engineering and technology constraints. And that is something that students and teachers need to know backwards and forwards before the students start designing their science experiments. So is everybody with me on that? Does that make sense? Okay. So now what's going to happen is that your students are going to submit their proposals to you, where they're making the case for how their team ought to get your flight slot. You're then going to convene a step one review board of STEM educators and local area researchers. There's a web page dedicated to how to put that step one review board together. And then your step one review board is going to use the proposal evaluation rubric to grade all the proposals. And the three with the highest of grades are designated finalists and are sent to us. We then convene the step two national review board at NASA close to Washington, D.C., and they will select your flight experiment from your three finalists and do the same for each of the other participating communities. Your flight team, therefore, is the ambassadorial team representing Mississippi area schools to move forward to flight operations. But I should stop here and say that, and this is going to sound a little weird, we did not care too much about the flight experiment when we were designing this program. Sure, students are vying for a flight slot just like professional researchers are trying to fly something on the International Space Station. That's an amazing idea. But from the vantage point of our goal for STEM education, what we wanted to do is immerse a local community of students in real experiment design, and they own that. And that real experiment design is constrained by real world engineering and technology constraints. And the students get to write real proposals against a real proposal guide with embedded citations and a bibliography. And they get to experience a real research proposal competition. That was our goal. And then after the flight experiment is selected, your flight team moves forward with 2 months of optimizing the experiment. And at that point, we have to lock in the list of fluids and solids that comprise that experiment. And that list goes to NASA Johnson Space Center in Houston to the Office of Toxicology for 4 months of flight safety review, because your microgravity research team has to go through the same doorways as any professionals to make sure that the experiment is not a risk to the astronauts or the vehicles. And then 2 to 3 weeks before launch, your flight team will fill and seal their ground control and flight mini laboratories and ship the flight mini lab to Houston. Rhodium, the commercial services provider, will take all of the SSEP experiments and put them into a single payload, hand that payload over to NASA. NASA will carry it to Kennedy Space Center and hand your experiment over to SpaceX. It will be put in a Cargo Dragon spacecraft on top of a Falcon 9 rocket, and it will launch from historic pad 39A at Kennedy Space Center, the same pad from which all of the Apollo missions to the moon launched in over 100 space shuttle flights. Your experiment is going to be carried 250 miles above the surface of the Earth and accelerated to a speed of 18,000 miles an hour, which is the same as saying it's moving 4.5 miles a second, or about 7 kilometers a second. It will rendezvous with the largest spacecraft ever constructed, the International Space Station, which is larger than a soccer field. The astronauts will operate your experiment 4 to 6 weeks on orbit according to your student flight team's protocol. So again, they are simply your technicians. And after 4 to 6 weeks on the station, your experiment will be put back into Cargo Dragon. Cargo Dragon will deorbit, land off the east coast of Florida. A recovery ship will pick the vehicle up, and all of the payloads will be pulled. The SSEP payload will be deintegrated. All of the mini labs will be photographed and inspected. And then your mini lab will be overnighted back to your student flight team for harvesting and analysis. You can send a delegation down to the launch at Kennedy Space Center to watch the bird fly. And I can tell you, if you've ever seen a launch in person, it is the most amazing experience. But if you're a student with an experiment on that rocket and it's going to be operated on the International Space Station, that's a life-changing experience. And I can also tell you, by the way, that all of your students involved in this need to put this on their CVs and resumes, because this is a really important experience for them. And I could tell you at the high school level, students have gotten into MIT, Columbia, Johns Hopkins, I can keep going, University of Chicago, because of this program. It was the focus of their college interviews. And so this is a really powerful opportunity for all of your students. The other thing I should tell you is that you can send a delegation to their own research conference, either at Kennedy Space Center or the Smithsonian in Washington, D.C., because we feel an absolutely authentic research conference should be part of this authentic program. And the last piece of this is, ever since human spaceflight began, a NASA astronaut crew would work with a NASA artist to create a graphic design that captures the mission objectives. And that's what's turned into the cloth mission patch that they wear on their flight suits. And it's the graphics package that brands all of the mission documentation. And so we will send up 2 mission patches with your flight experiment, which makes this an authentic STEAM initiative with A for art. And that means that you can open this up to hundreds to thousands of students beyond those students that are involved in the experiment design and the proposal writing phase. So you can open this up school district wide. It builds program-wide awareness for what you're doing here. And it involves art and design in an interdisciplinary way. And I can tell you that we just came out of celebrating the 50th anniversary of the Apollo missions to the moon, which are the most remarkable journeys the human race has ever taken in history. And we're now moving into the next phase, looking forward, for astronauts going back to the moon, to Mars, to asteroids, where we're going back into deep space. And so here we are in the present, celebrating the past 50th anniversary of Apollo. and inspiring the next generation of explorers through deep space missions. And so we feel very strongly that history teachers ought to be involved in the mission patch art and design competition. And all of this that I'm saying, everything in fact I'm saying today, is on the website. There's a page dedicated to everything mission patch for your art, design, and history teachers. And so the way to end this is to say that I said we would be giving you your own space program, but in fact, the better way to say it, which is more emotional and accurate, is that we are inviting all of you, we are inviting all of the students that are participating in the experiment design and proposal writing competition. And we're inviting all of the Mississippi Mills area school students that could be involved in the art and design competitions. We're inviting all of you into America's and Canada's space program in every sense of the word. This is not a simulation. This is real, and you're part of the space program right now. So does anybody have any comments, questions before we move on to the next chapter?
Jeff,
Yes.
it's Laura. I have a question about the rubrics. Where would we find those, like for the step 1 review board? Are you going to talk about that later?
Yeah, so what I'm going to do is I'm going to show you when we're going to the website where the page is for the step 1 review board guidance. It tells you how to set up your step 1 review board. And in the document library, we're going to go through what the documents are, but there is a proposal guide, which is the template for the proposal that students use to write their proposals. And accompanying that proposal guide is a background document for students, which talks about what a proposal is. And there's also an accompanying background guide for teachers, which includes the proposal evaluation rubric. So the background guide for teachers going with the proposal guide itself has the rubric for you.
Okay, that's great.
I'm sorry.
I did have a question about a rubric for the graphic for the flight patch. Are you going to cover that later, or?
There's no rubric for the flight patch. Everything with regard to what a flight patch is, how many students must be engaged if we're going to fly a flight patch. You can't just have like 3 students engaged. You're going to need 200 students minimum engaged in the competition or competitions. And there's no rubric for the patch itself. That's up to you. You can figure out how you put together the review of those patches. But one suggestion I can make is, why not reach out to local area artists and designers and have them be your judges, and you can figure out how you want to select the 2 patches. You should, if you do 2 patch competitions, you can have one at the lower grade level competition, like pre-K through 5, one at the upper grade level 6 through 12, because otherwise it's probably not fair to have, lower grade students competing against high school students. Does that answer your question?
That's great. Yeah. Oh, Jean has a question here sitting beside me.
So with respect to the patch, are patches, when the kids are, working on them and trying to design them as in their groups, is it specific to the experiments that are going to be selected, or is it just a generalized Mississippi Mills and something,
Yeah, so the way to think about it is, it has nothing to do with the experiment. It is a celebration of what this program means to your community, right? So this is about, you're going to have 2 mission patches orbiting the Earth every 90 minutes. And so what does that mean to you? What does it mean to be part of the space program? The history of space exploration, the future of space exploration, how Mississippi Mills area schools can be part of that. Does that help?
yes, thank you.
Any other questions?